So this will be the third lecture out of chapter 17. So in this lecture, we're just going to work some problems just to apply some of the material that we covered in the first two lectures. So let's take these reactions and predict the major organic product. So you recognize this is the recipe to put a bromine on the benzene ring. You just got to know where it goes. And so how do you know that? You have to determine if the group on benzene is an OP or a metadirector. And so one way to do that is recognize that nitrogen is attached to benzene, has a lone pair of electrons on it, so it's an OP director. So it wants to put the bromine here, here, or here. So A, those two positions are equivalent, and B, so it's an O, so you have to show both. So if it's an OP director, then you always have to show both as possible products. So you could put the bromine there. Or you could put the bromine there, para to it. So if you did this reaction in lab, you would get a mixture of ortho and para products, and you would have to separate them from each other. You wouldn't get much meta substitution because that group is an OP director. Okay, so that's the recipe to put a chlorine on a benzene ring. You just have to know where it goes. So now you got two benzenes. So now you have to decide which one does it go to. Well, so on the benzene, so we'll call this benzene ring A and this benzene ring B. So for benzene ring B, that's the atom that's attached to it, and it has a lone pair, so that's an OP director on this ring. And so for ring A, that's the atom that's attached to it. That has a positive charge on it, partial positive, so that's a metadirector on this ring A, all right? Okay, so it's either going to go here, ortho or para to the oxygen, or it's going to go here, which is equivalent to there, meta to that. Well, which ring is activated? Well, this ring is activated, right? Because the oxygen is an OP director, and that's an activator, whereas all metadirectors are deactivating. So this ring is deactivated. So the ring that's going to react the fastest is the one that's activated. So your product, so the chlorine is going to go on this ring then at the ortho and para positions. And again, you would have to sketch both. So you could put the chlorine there, or if you ever get tired of drawing benzene, you can just call it pH, phenyl. So it saves you a little bit of writing time. So you would make those two products as your major organic products. And again, if you're working in lab, if you wanted the ortho, you would have to do some purification to separate the para isomer out, or vice versa. Okay, so now this is the recipe. So you're just going to put a nitro NO2 on the benzene ring. You just got to know where it goes. So two benzene rings again, so A and B. So this is an activator, and so OH is an activator on ring B, and benzene rings are also activators. So it's an activator on ring B also, so ring B is going to be the one that reacts. And so the OH is an OP director. It wants to put the nitro group ortho or para to it. The para position is blocked, and this is also an OP director, so it wants to put the nitro group there. So which one is a better OP director? That would be the alcohol, OH. So the alcohol wins. So your major organic product would be that, and well, that's it, right? The para position is blocked. So that would be your major organic product. Okay, so in this problem, so this is going to put an SO3H on the ring. You just got to know where it goes. So that has a positive charge on it, so that's a metadirector. So it wants to put the SO3H there or there. Those positions are meta to it and they're equivalent to each other. So it doesn't matter which one you put it at, it's the same. All right, so that would be your major organic product. Okay, so for this next one, so what you want to recognize is that is not benzene, right? It's cyclohexane, so nothing's going to go onto that ring. It's your substitution is going to occur on this ring. And so what you have to do is look at that atom. That atom is partial positive, so that's a meta director. So that's going to want to put the group there or there, and of course those positions are equivalent. So now you just have to know what to put on the ring. So if you do this, that's a Friedel-Crafts alkylation. What do you know about Friedel-Crafts alkylations? Is they make carbocations, right? This would pull the chlorine off to make that carbocation. So you have to look out for a rearrangement. So that carbocation is going to rearrange by a 1,2 hydride shift. So your positive is now on that tertiary carbon. So that's the carbon that's going to attach to benzene. So that carbon meta to the ketone is going to be the one that's attached to the carbocation carbon. All right, so that would be your major organic product. Okay, so if you're given a reaction presented like this, so you have a 1-to-1 mixture of nitrobenzene and this methoxybenzene, and you do a Friedel-Crafts acylation, so that's just going to put that on the benzene ring, right, because you make that carbocation. But which of these rings is going to, so nitro is a meta director, it would want to put it there. This is an OP director, it would want to put it there. But this, all meta directors are deactivators. So that ring is deactivated, right? Oxygen has a lone pair, so this is an OP director and this activator. So the nitrobenzene is not going to react. The methoxybenzene or anisole is going to be the one that's going to react. Let's draw this better. So you would make that, and you would make that as your major products. Okay, so this one's a little tricky. So if you remember, so that's going to pull chlorine off, right? To make that carbocation, so what do? So I didn't give you anything for it to react with, but I did because there's a benzene ring right here, and that has a lone pair, so this is an OP director. So that wants to put an electrophile at those positions, or ortho para to it. So this is, since this is just going to be an intramolecular reaction. So you're going to make a ring. So anytime you make rings, I recommend you number. So that's going to be, so let's see. So basically what's going to happen is you're going to do electrophilic aromatic substitution on this carbon. So that's going to be attached to that carbon. So you're going to make a 1, 2, 3, 4, 5, 6 membered ring. Okay, so this is carbon, this is 1 and 2 of the rings, so you're going to have a 6-membered ring attached to it. So 2, so 3 is an oxygen atom, 4, 5, and 6 has a CH3 on it, so that would be your major organic product. Okay, so let's apply what we've covered so far in this chapter to do some organic synthesis. So let's do 3 synthesis problems. So we need to put a chlorine on a ring, so we know the recipe for that is CO2 FeCl3, right? We want to put a ketone on the ring, so we know the recipe for that is Friedel-Crafts acylation. So it's just a question of which one do you put on first. So if you did the Friedel-Crafts acylation first, and you made that. So then you tried to put the chlorine on. Right, does it work? And the answer is no, it does not, because that carbon is partial positive, so this is a metal director. So that would want to put the chlorine here or here. So if you did this, then what you would make is that, which is not what you want. So the point being, in organic chemistry, sometimes the sequence of reactions matter. So what you would have to do is put the chlorine on first. And then chlorines are OP directors. So that's going to want to put the ketone at one of those spots. So now you do the Friedel-Crafts acylation, and you make that. You make the ortho product. Of course, you also make the para product, so you would have to do a separation, but you would make enough of the, so you would make some of the ortho product as well, and you would just have to separate that out. But if you did the this sequence, then you would make almost none of the ortho product. So that would not work. Okay, so for this reaction's got a little twist in it as well. Okay, so you want to put a bromine on the ring, so the recipe for that is Br2 FeBr3, and you want to put a propyl group on a ring. Oops. And so what you want to recognize is this will not work, right? Because that would rearrange, make that carbocation, which would rearrange to that. And so you would end up putting an isopropyl on a benzene ring and not a propyl. Furthermore, this is complicated by the fact that this is an OP director and this is an OP director. So how do you get two OP directors on a ring meta to each other? Well, the key is to know how you're going to get that on the ring without rearrangement. And the way you're going to do that is you would do a Friedel-Crafts acylation first. Right, so now you got the 3-carbon chain on the ring with no rearrangement. And what's significant now also is that that carbon's partial positive, so it's a meta director. So now would be a good time to put the bromine on the ring. So that would direct the bromine to there or there, and those positions are equivalent. So now you got the bromine on the ring, so now you can get rid of the C double bond O. So if you remember the reagents that will reduce C double bond O all the way to CH2, you could do the Clemmensen reduction, mercury, zinc, and HCl. Or you could have done the Wolff-Kirchner reduction, doesn't matter which one. You don't have to show both on a test. You just have to pick one and you're done. Your synthesis is done now. So that reduces the CH2, C double bond O to CH2 to make the propyl. And now you've got the propyl and the bromine matted to each other with no rearrangement. Okay, one more synthesis problem. Just because I know synthesis is really difficult for a lot of students, because you have to really know your reactions. You have to have all of your reactions memorized so that you can just pull out one reaction out of your head that you need to finish the synthesis off. Okay, so if we wanted to synthesize this, well, how can you get a CN on a carbon Well, one way that you could have done that is you could have had a tosyl group there. You could do an SN2. Right? So if you had that compound and you reacted it with potassium cyanide, Cn- would come in and kick off the OTS group. So how could you get an OTS group on a ring on that position? Well, you could have had an alcohol there. And you could have reacted that with toluene sulfonyl chloride. Well, how could you get an alcohol there? Well, you could have had a ketone there. Right, if you had that ketone and you reduced it to the alcohol. So if you remember, you're reducing agent, so how could you do that? Right, if you had that ketone, you could react it with lithium aluminum hydride and then do an acid quench. Right, if you remember that reaction from a few chapters ago. And then where could that ketone come from? Well, that's a chapter 17 reaction, right? You could have done a Friedel-Crafts E solution. That would be one way to do the synthesis. So make the ketone, reduce the ketone to the alcohol, convert the alcohol to the tosyl leaving group, and then do your SN2 reaction. And there are other ways you could have gone about this. That's just one of the ways. So quickly, another way you could have done this. Right, you could have put the ketone on, and then you could have reduced the ketone. Put the propyl chain there, and then you could have done a free radical bromination. Put a bromine on there, so now that's a leaving group. And then you could react with the nucleophile. And do an SN2. Similar, at least the first step is similar, and then after that it's a different pathway. So both are at the same number of steps, maybe 1, 2, 3, 4 steps. 1, 2, 3, 4 steps, so both 4 steps. So which one do you do in lab? You do the one maybe that's going to give the highest yield, or you do the one that you have the reagents in the lab so you don't have to buy anything, or you do the one where the reagents are the cheapest, so that you keep your expenses as low as possible. Right, there's lots of factors. Or you do the one that's going to have less environmental impact, less toxic stuff that you have to deal with, because if you have to dispose of it, then that adds cost to your synthesis. So there's lots of factors that would go into deciding which synthesis you want to do. But certainly yield and time and money would be, and environmental factors would be all factored into the synthesis that you choose. Okay.